All right. Differential equations. Chapter 9 is about differential equations. What's a differential equation? Well, a differential equation is an equation that has some derivatives in it. And it could be just one. Like, for example, this is a differential equation. What is the solution? We would say the general solution. I mean, equations have solutions, right? So, what's the solution of this one? The general solution of this, well, that would be an easy one, right? You just, let's see, that would be y equals x squared over 2 plus c, right? It's just, we just take the antiderivative. So that's nothing new. And if we were given a point, then we could find a particular, what is called a particular solution, right? We could, in other words, solve for c. All right, but the new thing is this. We're going to start seeing differential equations that have, this is kind of like the opposite, the chain rule. When we learned how to do integration, we learned how to do the chain, U substitutions. And U substitutions deal with like the chain rule backwards. And then we did integration by parts, which is kind of like the product rule backwards. And we have all these different tricks. Well, this one is sort of like implicit differentiation backwards. In other words, what do you do when there's x's and y's over here? For example, what if we had something like this? dy dx is equal to 2xy. So here's a derivative, but it's not just equal to some function of x. It's equal to x's. We've got x's and y's over here. Now, in our curriculum, we are only going to deal with what are called separable differential equations. And the separable means that you will be able to, just doing a little bit of algebra, maybe factoring and dividing, stuff like that, just simple algebra, you will be able to get all of the things with y's onto the side with the dy, and all of the things with x's with the dx. Okay? So I'm going to do that. I'm just going to do a little bit of multiplication. You can see what's happening. I'm going to move the 1 over y, I'm going to move the y to this side, and leave that with the dy. And then I'm going to move the dx up to the other side. That's always going to be the same move. We'll always move the dx over here. Okay? So that's just a little bit of algebra. You can pause for a second and examine that if you like. And then I'm going to take the antiderivative of both sides. Okay? Notice that the variables match up, right? So that's good. That means, what's the antiderivative of 1 over y? Well, it's the natural log of the absolute value of y plus c. And what's the antiderivative of 2x? It's x squared plus c. Well, I have two c's here. Those are not the same c, so I better make some kind of distinguishing feature there. But of course, you know, these are just constants and we don't know what they are. So what's to stop me from just like subtracting c1 from both sides and getting natural log y is equal to x squared plus, I mean, c2 minus c1. Well, that's just some other constant, right? Whatever that is. So the convention will be, that's the only time I'm ever going to do that. I'm only ever going to put the plus c on the right-hand side. That's the way we usually deal with the plus c. Now, if I wanted to solve this for y, then how do you get this? Well, you could do e to the natural log y is just y, and then e to the x squared plus c. So there you go. But one more thing that we usually do, or sometimes do, especially when it's this kind, this is a common result that we end up with some kind of natural log thing over here, and it turns out to be some kind of exponential function here. From algebra, recognize that e to the x squared plus c is the same as e to the x squared times e to the c, right? If you had x to the something times x to the something, you'd add the exponents. So I'm just kind of going the other direction with that rule. And e to the c is just a number too. That's just a constant. So we could rewrite that, instead of having our plus c up here, the e to the c is just some other constant. So that's our general solution. And again, if we had a point, we could plug in the point and figure out what that c is. Okay? So that's your the basics of solving what are called separable differential equations. Let's try a couple more examples. So this time let's try one that has when we're given a point. So dy dx is equal to, let's do x over y. And let's say it goes through the point 2, 3. Okay? So the directions here would say we're supposed to find the particular solution to this differential equation goes through this point. Okay? So we'll do our separation of variables thing. Multiply the y up here. That gives me y dy is equal to x dx. Take the antiderivative of both sides. Antiderivative of y is y squared over 2 equals x squared over 2 plus c. We would have had a c on both sides, but I've just consolidated them over there. And now if you wanted to, also notice that, because this is just a constant, I could multiply the equation through by 2. You don't have to do this, but it's going to make it a little bit easier to deal with. What's 2 times a constant? A constant, right? And then we plug in our points here to solve for c, and I get, let's see, 3 squared equals 4 squared, 2 squared plus c, so c is equal to 5. So my solution is, depends on how you want to write it. I guess you could write it as y squared is equal to x squared plus 5. If you can solve for y, that's a good thing, but we can't really solve for y here. This is not a function. So, I mean, you could say, well, y equals plus or minus the square root of x squared plus 5. That's the same thing, but we really, there's no advantage writing it like this than having it like this. So if you can solve for y, then you should. Otherwise, probably not. And you might want to just take a second to reflect on this and see if you know what this thing is. And maybe if I write it in a different form, let's see, if I write it in the form y squared minus x squared equals 5. Do you recognize what it is now? What if I divided the whole thing through by 5? Y squared over 5 is x squared over 5 equals 1. Now do you recognize what it is? It's a hyperbola. So it turns out this is the differential equation for a hyperbola. This would be a hyperbola that opens up and down, because the y comes first, and it's little, when we make the little box for it, this would be like the square root of 5, this distance right here. And it would do this, and it would make our asymptotes, and it would go through those points, and so on. So I don't know if you remember your conic sections, but that's what that is. So this turns out to be the differential equation for a hyperbola. Cool. All right, let's do one more. Here's a common situation. Well, actually, I'll do two more quick ones. Dy dx is equal to ky, some number times y. And I'll just solve this one in general. Now let's think about what this says before we do anything. This says the rate of change of y with respect to x is directly proportional to y, not to x, but to y. If this is kx, then it would just be kx squared over 2 plus c. But this is directly proportional. The rate of change is directly proportional to y. Or in other words, the rate of change, and actually I'm going to make this a rate like a time instead of dx. Sorry about that. Should have done that to start with. So we can think of it as something changing with respect to time. So I've got some graph. If I wanted to graph this, the graph of it would look like, here's the y, whatever this stuff is, and here's time, right? So the slope of the graph is directly proportional to how much stuff there is. And we have talked about this in class before, but let's just go ahead and solve this and see where it leads us. So separating variables, getting the 1 over y over here, dy is equal to, I'm going to leave the k over here, k dt, and then integrate both sides. Antiderivative of 1 over y is natural log y. Antiderivative of k is kt, right, because k is just a number, plus c. And then I'll raise both sides to the, or do e to the both sides, so I can get y over here is equal to e to the kt plus c. But using that algebra trick again, the e to the c, I'm just going to bring that number out to the front. That gives me y is equal to c e to the kt. And you might recognize this. This is actually just the Pert formula, where k is the rate of growth and c is the amount of stuff that we're starting with at time 0. So this is where the Pert formula comes from. Why does the Pert formula work for population growth, radioactive or half-life decay, and money growing in a bank account? Why does it work for those things? Because those are all situations where the rate of change is in fact directly proportional to how much stuff you have. If we're talking about money, then the rate of growth of money in your bank account is directly proportional to how much money there is in there, right? It's not proportional to time, it's proportional to your money. And if you have the growth of a population, then the rate of growth of the population tends to be directly proportional to how many members there are in that population, right? And so on. So, so what does it look like? Oh, wait, it's an exponential function, looks like. Ooh, that's a pretty lousy looking exponential function, right? It's some version of e to the x, right? All right. And then one more. This is a little bit of a foreshadowing of what's coming. I think it's in section 9.3. I won't do the crazy one, but I'll do another. Here's one, dy. I'll do it with respect to time again. What about when the rate of change of something is proportional to something like this? Well, let's just do that. Let's just do 50 minus y. So in other words, the rate of change, if you don't have any stuff, then the rate of change is 50 if you're at 0, right? If your y value is 0. But the more stuff you get, the more the rate of change goes down, until as you get closer and closer to 50, your slope gets closer and closer to 0, right? So we might imagine that if we graphed something like this, that as the amount of y stuff gets closer and closer to 50, the slope gets closer and closer to 0. So we might imagine that there's like a horizontal asymptote here at 50. And that is actually correct. Right? Because as we get closer and closer to 50, the slope gets closer and closer to 0, because 50 minus 50 is 0. What if you start higher than 50? Then it does the same thing. It just approaches it from above. So let's try to solve that. So let's see, that gives me 1 over 50 minus y dy is equal to dt on the other side. The antiderivative of this, you've got to be careful here. It's negative natural log of 50 minus y. Right? Why is the negative there? Because of the negative in front of the y here. You could do a u substitution to do that antiderivative if you want to see where that negative comes from. But it's a real common mistake to forget that. And you wouldn't do anything like that, of course. The derivative of 1 dt is just t plus c. Now I'm going to go ahead and move the negative sign over to here. So that gives me natural log of 50 minus y is equal to negative t. It could be minus c, but it's just a constant, so that you can leave it as plus c. And then we'll do this. That gives me 50 minus y is equal to, I'm going to do the same trick where I bring the c out to the front over here, c e to the negative t, and then solving for y, that gives me y is equal to 50 minus c e to the minus t. And you can check that out, and that will in fact have a horizontal asymptote there. So there's some examples for you.